Good evening.
Good evening.
Today we will be talking about Fourier series. So many times I'm getting very frequently asked question, why is it useful? So this is how practically you can apply Fourier series. And you obviously can find some applications of Fourier series, but this is not the reason we learn it because the applications are very narrow. You don't have that many applications of Fourier series. But understanding of Fourier series gives you opportunity to understand discrete Fourier transform, which is essentially the same Fourier series but in discrete time. And if you understand that thing, for you it will be much easier to understand discrete Fourier transform, which is used almost in all signal processing everywhere, in all applications of signal processing. And if you just Google for it, you'll find millions and millions of papers published on applications of Fourier transform. And this is basically the fundamental theoretical basis for that thing. So here all of those formulas should be available for you, and they are available in formulae pages, also in the lectures. And this is just to refer to those formulas where we will solve some questions. We will refer to those points. Now, the idea of Fourier series is essentially very simple. You're trying to write any periodic signal as sum of sinusoids, which is cosine or sine functions, with different amplitudes, with different frequencies, but those frequencies will be basically related to periodicity of that function. So we will compute how it relates, and only for periodic functions you can write something like that. So you can represent any given function x of t as some constant, and we're dividing that constant only for convenience, because we don't want to write separate formula for a0. It will be the same thing, just 1 over t. If you just define the entire thing as a0, so if you define that as a0 divided by 2, you can use exactly the same formula for all ak, including 0. Okay, just for convenience sake, it's more convenient to divide by 2. So this is just some given constant. Equals to that constant plus some coefficient, which is number multiplied by cosine of something, plus another number multiplied by sine of that something. Okay? Now, to compute those coefficients, you have two formulas. That's it. Everything else is just technical, you solve those integrals. Now, alternatively, you can represent it as complex Fourier series. This is exactly the same thing like this one, and you can convert one into another using some formulas. And then it will be represented by sigma from minus infinity to plus infinity. Pay attention to the difference. This is starting at 1. This one is minus infinity. But this coefficient will be not real, but complex. Again, we are talking about representation of complex signals or real signals in that one. This one is only for real signals. You cannot represent any complex signals with that one, because this is, after all, just real functions with real coefficients. This one is complex functions with complex coefficients. So it is allowing you to represent wider spectrum of different functions, including complex functions. Again, on the question whether you use complex functions, you have some in communication, not very frequent, but you have some. Okay? So using that one. Now, the idea is that if I'm giving you some function, you cannot write that right away. You need to find those coefficients first. And this is how you find those coefficients. Just using that kind of formula. Okay, so a few more things that will be useful for us. It's just how you convert one type of coefficients to another. So you can write those coefficients in that sequence as a function of those coefficients, or vice versa. So this will be 0.5 k equals 1, 2, and 1. 0.5 0 k equals 0. So pay attention that I'm writing that one as minus, right? Negative number. Why? Because k is negative. So for example, if k is minus 1, this will be a1. And here you don't have any negative coefficients. All these coefficients are positive for this, because k starts at 1. You don't have any A of minus 1 or something like that. This is why you need here negative index just to convert them into symmetric positive ones, like mirror image. Okay, and another one is Parseval. This will be very useful for power computations. Basically, it says that for your periodic functions that you are measuring, your average power in frequency and in time are the same. Which means this is definition of power, right, over some period, which is kind of average energy per time. Since I'm starting from minus t to t, so the overall interval of time is 2t. And I'm dividing by that interval, so it's average energy per your period, t, equals to sum of all of those coefficients together. And those coefficients are essentially spectrum, right? So Ck is spectrum of our signal, and absolute value of that is amplitude spectrum. Square of that thing is power spectrum. So basically it's sum on power spectrum. So total power on that interval from minus t to t is the same thing in time and in frequency. We're using those coefficients. So it's very easy to compute, especially for trigonometric functions where you have only a few of those coefficients and everything else is just zero. Okay, so when you have that case, you will use that formula to compute the energy instead of computing integral of something big trigonometric in square, right? Which is not very convenient. Yes. This is the overall idea. Now, you will have a few types of questions here. So, any questions on the theoretical part? All you need to do, like, this is all of the theories that you basically need to know on all of the Fourier series, and everything else is just using those formulas in some tricky or smart way. Depends on the question. And now I want to talk about types of the questions that you will have in general in that domain. So, question number one, find trigonometric series of such and such function, which is given by some formula, or given by some plot, or given by something. Now, so this is one type of question. Then similarly, of course, you have the same thing for complex Fourier series. Find complex Fourier series of given function by some graph or by some formula. Another question is find power of that signal. So you already know that finding power of the signal is just computing that kind of integral, right? But in most cases, I would not recommend using it. In most cases, okay? Because this will be some complicated trigonometric function. You put in that square in the trigonometric function, which makes it even more complicated. And then you need to compute integral of that. Obviously, you have table of integrals, but this will not be really helpful if you have square of all kind of cosine 2 theta plus whatever. Okay, so it's too complicated to compute that integral, especially if you get in that kind of question on the test. So not recommended to use a formula, the left part of that formula. It's much more convenient to get those coefficients and then to compute power, just adding them together. Square. Okay, another question is find signal average, which is basically average of the entire signal. You have some sort of signal, you want to find middle line. So now you know what average is, and you want to find it in some easy way when you have already Fourier series, because this question generally will come after you compute all kind of Fourier series. So this question is essentially trivial when you have Fourier series, because this is average. This is kind of bias of the entire thing, like DC value, right? It's like in voltage, you have DC value and DC bias. This is your DC bias. It's constant wave, which is added to things which have average zero, obviously, right? Cosine has average zero, and sine has average zero, no matter what frequency you have, right? All of them have average zero. So if you average the sum of those, it will be zero. The only thing which left is that thing outside. And this will be your average of your signal, A0 divided by 2, which is the same thing as C0. Okay? Those like first coefficients at origin. Those coefficients will give you average value of the signal. And then many times you need to sketch the spectrum. Spectrum, as you've seen, in most cases is amplitude spectrum, so it will be absolute value of that thing. Sometimes phase spectrum, which is angle of that complex value. And then you need to plot those dots. You just need to compute them one by one. Okay, or you need to just compute them by formula. So you find the formula for absolute value of that thing, and then you just plot it. Hopefully it's easy enough. Now, not always. We will see some examples. Okay, so let's start with algorithm, how we approach that kind of problems in general. I will try to write some algorithm which will help you maybe to understand better how you decide which way to go. Because to find Fourier series, sometimes you can use the definition like that, like directly using those formulas, computing those integrals, and you don't have any other choice. And sometimes you have trick. If something is much easier than that, you can bring it to that form without solving any integrals. And then you can compare coefficients, which is much easier generally than computing that kind of integrals. Okay, you just need to write it in trigonometric form using trigonometry. This is why you need background in trigonometry. Like all those relations between angles and so on, which you need to use to simplify some expressions that you are given, to bring it to that form, as sum of cosines and sines. And then from that sum, you'll find just the coefficients. That's all you need to do. So we will see some examples of that. So this is how it works. Step number 1, find t, which is periodicity of your given function. Okay, I'm giving you some function, you find me what is the period of the function. Now, next one will be question. You're asking simple question, is a trigonometric signal? And by trigonometric I mean something based on cosine and sine and their combinations of some kind. So if it is yes, you go that way. If no, you go that way. So here, for example, I don't know. Something of that kind. Okay, so you have some expression which is written as a function of sines, cosines, of all kind of angles, maybe they're squares, cubes, or whatever. Some powers, or some other expressions related to that, which you obviously can somehow simplify using trigonometric identities. Right? So you can write it as sine of alpha t and cosine of beta t multiplied by all kind of coefficients, or multiple terms of that kind, okay, just by simplification of that expression. Or no, it could be something else. Let's say some piecewise functions which are not kind of completely analytical, or given as a plot, which is given graph image of the function itself. So obviously you cannot do trigonometric simplifications for that kind of plot. You have no choice. Now, in that case, this case is kind of simpler. You need to use definition. So you're computing Fourier series based on those formulas, so using integrals and so on. And in most cases, if you get something like that on the test, the function itself should be very easy to work with because computing integrals on the tests is not easy. Okay, it takes time. So it should be something very elementary in terms of plot. Something very simple to compute. Now, in that case, you need to simplify. So the step will be you need to simplify. So you essentially simplifying just that kind of form. Sines and cosines and the sum is all kind of angles multiplied by all kind of coefficients using trig identities. We will see some examples of that one. After that, you find AK and BK by comparing coefficients. So what you do is basically explicitly writing that entire thing, I mean opening that sigma to actual terms, and you will have of course infinite sum. You don't need to write all the infinite number of terms, but only relevant terms. Okay, with specific contents here. You will see how we do that. And then you just compare those coefficients to whatever numbers you've got as coefficients to the same kind of cosine. So if you'll have here cosine of 2t, and there you'll have 5 multiplied by cosine of 2t, then this a with that k will be 5. This is how it will work. So you find each of those. And then you can compute CK if you need to. You're asked to compute trigonometric and complex, and this is generally how it happens. You get both of them. You need to compute both. By using that formula. So you have already those coefficients A and B, just computing coefficients based on that formula, or, which is sometimes even more efficient, comparing coefficients to this one. You're writing every sine and cosine in your trigonometric series using earlier formulas. Remember those? As exponent j t plus exponent of minus jt divided by 2 for cosine, and divided by 2j is for sine. You have all those formulas to convert basically cosine and sine into exponents, right? So each exponent with specific power will have coefficient, and those will be those coefficients. We'll see also some examples of that. Okay, so from that one you're computing using that formula or using just comparison of coefficients. And then from that one, you can compute power if you need power. We're computing power just by adding all of those coefficients absolute value squared. That's it. Because you will have, for trigonometric things, you will get finite number of non-zero values here. Most of them will be zero. You just add in those which are not zero. And you put them into power. Now, in that case, if you want power, you have to use definition, no other way, unfortunately. So you have to use an integral on x squared dt divided by 2t. Okay? if you're using definition for everything, which is, again, rare case in tests. Most of the cases you will go that route for solving any questions in that domain. Any questions? Now we will solve a few examples which will not fit into that algorithm. Because I want you to use common sense when you're doing your computations and not only just using step-by-step instruction. Engineers should use that common sense. So this algorithm works in most cases, and for whatever you will see in your tests and so on, most probably this algorithm will work fine. But sometimes you need to know that you not always can go that route, for example. Okay, you also have to take that route. So let's see one example which kind of contradicts what I said here. Not exactly, but well, so this is our example. Find complex Fourier series of x of t, which is absolute value of cosine phi t. Okay? And then you need to find average value of that thing to draw, to find power, to find all the standard ratios, to draw spectrum, amplitude spectrum, phase spectrum, that kind of things. Okay, but let's start with complex Fourier series of that kind of signal. So if you're using that kind of algorithm, you'll go here. Is it trigonometric signal? Yeah, kind of. Yeah. It's cosine, right? Cosine is trigonometric function. But can you simplify it to the sum of cosine of sine? No, you don't have any trigonometric identities with absolute value of cosine, right? You can work with cubed, you can work with squared, you can work with double angle, triple angle, and whatever angle, but not absolute value. You don't have any identities that will simplify that into something simpler or sum of cosines or sines of some kind. So you cannot do that, right? Now what?
Why not just
Just
illustrate the
page
complex?
empty. Yes,
Why not just convert it to complex?
convert it to complex. Okay, let's convert it to complex. So this equals e to the j pi t plus e minus j pi t divided by 2 absolute value of z. Now what? This is cosine, right?
Yes.
Yeah.
So absolute value of 2 is 2, so you can skip that one. But what is the absolute value of that sum? So both numbers are complex, so they are not really positive or anything.
I'm using
Right, that you can drop the absolute value. This is not positive, it could be negative, or could be complex. Depends on the value of t.
I mean, using Euler's, can we go back to cosine sine?
You use Euler, you get back z. You get cosine.
Right.
This is what Euler says, right? Because we developed that one from Euler
Yeah.
theory. You get back, I mean, after some long computation, you will get back the same cosine. Like it in MATLAB. MATLAB will give you a good solution. In tests, you're not able to use MATLAB. Unfortunately, maybe next time. Hmm? Call friend? Call. Let's see what friend says.
I wouldn't trust him. I don't have friends. Come on, dude. Come on, dude.
Okay, basically, what I have to say is that you have no choice, you have to use actual definition of the Fourier series. And this is still trigonometric signal, but we don't have any good simplification which will help us to get that route, which is easier in most cases.
Can you agree with that? Or do we have to
You
go back
can.
to cosine?
So let's see how we actually do that. First of all, step number one, we need to find t. So what is t of that thing?
So, 2.
So what is a cosine basically? Can you draw it? Like that.
It's 2 pi over pi, right?
Like that. Right. So what will be the number here where it hits the 0? It will be 1. Because cosine of pi is 0. Cosine of minus pi is also 0. So it repeats basically, no, it's not, it should be half, right? The total period should be 1. Minus. Right? So cosine periodicity of cosine pi t is basically how many? 2.
Yes.
So cosine absolute value where you're flipping that part up should be half of that. So it's total how many t? Like, what is the size of the t?
Because you flip it, so that's 1.
What?
1. Okay. Now, is it proof that this is how it should be? How do you know that this is correct? I mean, this was guess, basically. You need to prove it. And the proof will be that x of t plus t, which is xt plus 1, equals xt. That's what you want to prove, right? Then you prove periodicity. Then you're saying this guess was good, if this is true. Let's see. So you're saying that cosine absolute value pi t plus 1 equals absolute value of cosine pi t plus pi absolute value. Right? Is it true?
Yes,
Why?
because two pi t would make it like a negative, but then it's absolute value, so it's still.
I mean, if you put in 0 for t, you get the same.
So let's see. If you're adding pi, you're basically adding half of the period, right? So this is what pi means. So cosine will be 2 pi period, right? So if you have cosine, which looks like that, it will be 2 pi period. So 2 pi here, right? Now, if you're taking absolute value of z, this one will be flipped here, right? So it repeats basically every half a period of regular cosine, which means that this cosine will be exactly like that one if you're removing that pi. So this will be absolute value of cosine pi t, which is the original x of t. Is that clear? Or we need deeper investigation here? Okay, so it's a low level of noise, probably it's not clear, right?
It is clear.
Is that clear?
Crystal.
Okay. So we found periodicity, okay? This was just step number 1. Now we need to apply the actual formulas. So you want formula for that thing. So you want ck equals 1 over t, integral from 0. In that case, let's write it directly because we have the formula already there. So t will be 1, right? This is our period. From 0 to 1 of x of t, which is cosine of pi t, absolute value, times exponent minus j k 2 pi over t will be just 2 pi. And then t. dt. Now, is it convenient to compute it in that way? Remember that we can shift the integral to any location of the interval we want. So where it will be the most convenient interval?
Negative 0.5 to 0.5.
Yeah, so we want to shift that instead of 0, 1, we want to shift it to negative 0.5, 0.5. Why? Because in that case, you can remove absolute value. It's always positive there, right? So if you're taking that part from here to here, this is always positive for the entire cosine, right?
Right.
The original cosine without absolute value will be positive in that interval. And this is exactly our period that we want. So we replace this one with minus 0.5, this one plus 0.5. Any questions on that? Okay, just shifting the entire thing. And then I'm removing absolute value. So let's compute it. How will you compute that thing? This is tricky integral to compute.
Parts?
Not too much.
Yeah.
Generally, we'll have many integrals of that kind where you have some trigonometric stuff multiplied by some exponential stuff. You want something like that. You want to convert all of the trigonometric stuff into exponential. Why? Because it's very easy to do integrals of exponential stuff. We like integrals of exponent, which is the exponent itself. And if you have exponent of something times t, you just divide it by that constant. Okay, so it's very convenient to use exponential stuff. So let's write the cosine in exponential form. Again, integral from minus 0.5 to 0.5. Instead of cosine, we're writing exponent of j by t plus exponent minus j by t times exponent minus j k 2 by t dt. Now we have basically sum of two integrals here. So you can take that first part times that second exponent. Remember how you multiply two exponents? You just add in the powers, right? And then the second exponent is the same thing. So it will be z part multiplied by z part plus z part multiplied by z part.
Yeah.
Okay? So you'll have basically 1/2 can go out, no problem. Exponent, what is the common part here? J by t, and here j by t. So you'll have j by t, and here you'll have 1 minus 2k, right? Something like that. So I just took common thing, which is j, pi, and t, and left with minus k twice k. And here, just nothing. It's like 1 minus 2k times j by t. And I can divide that into multiple integrals. Plus 1/2, the same integral. And I can write it as one integral or two integrals, it doesn't matter in that case because integral is linear operator. So you can divide sum of integrals, sum of function of sum into sum of integrals. And here you'll have exponent minus j by t times 1 plus 2k. Okay, so far. One half. The first one will be exponent, and you need to divide basically by all of that part, j by 1 minus 2k. So it's 1 divided by j by 1 minus 2k times exponent of the same thing. Integrals from from minus 0.5 to 0.5. Okay, that's how you compute that integral. Plus 1/2, and here I'm dividing by all of that part except t, which is 1 over minus j pi 1 plus 2k, and then you get the same exponent. Again, from minus 0.5 to 0.5. Now we continue that thing. Okay, let's see. It's okay so far. This looks fine. Now you have first one is 1 over 2j pi 1 minus 2k. And now you have exponent at 0.5 divided by exponent at minus 0.5. So what is that exponent at 0.5? Let's see. So it will be like that. Exponent j 0.5 pi times exponent minus j pi k. This is the first one. So I'm just multiplying that one by 1 and then that one by 2k. I'm just opening that exponent into multiplication of two exponents. Okay, at 0.5. I'm just applying t equals 0.5, so it's j pi 1 0.5 minus j pi 2k 0.5, right? So 2 with 0.5 will get 1, it will be minus j pi k. Right, this is the second one. Question so far? So this is just that part. Now, minus, similar thing, just with minus j 0.5 pi, j pi k. Okay, so I'm putting instead of plus 0.5, I'm putting minus 0.5. To convert that one with the same thing with minus, and that one the same thing with plus. Okay, so this is the second part. When I'm subtracting from that one, I'm subtracting that one. Now plus 1/2. So it's basically I can replace it with minus. So this is minus j here. So it's minus here, minus here. Twice j pi 1 plus 2k, and here 1. And now the same thing here. Minus j pi 0.5 e minus j pi k minus e j pi 0.5 e j by k. Okay, let's try to simplify it. I want to get to some sort of simple thing here. So what is that thing? Remember how it looks like? If you have that circle, this is j, this is 1, minus 1, minus j, but it also angle pi half, pi, minus pi half, and 0. Yes.
Why is the, on the second one, the e to the negative j by k, why is that a negative, not positive?
Is that one?
The left one.
This
That
one?
Yeah.
Why this one is negative?
Well, I'm
So you
saying,
have, because of that.
right, and then when you split them, oh wait, I was thinking the second one, I guess.
So
One-
this is the
why
second
shouldn't
one is
one
here.
of them be
The
positive?
second one is here, and this one is here.
Okay, yeah.
So it's like put 0.5 instead of t here.
Right.
So you'll have minus j pi 1 0.5, which is
Right.
negative, right? This
Right.
one.
Right.
And then you'll have minus j pi 2k 0.5,
Makes one.
which is still 1 times k times
Right.
pi times minus j. Right, so it will be also negative. And both of those will be obviously positive because this is the same thing with negative sign. Okay, now let's simplify it. So what is e to the power j 0.51?
J.
So
One
we
half.
also have to turn off that as 1, so it's unit symbol.
It's just J.
Right.
Or is J?
So it's j. This one is
J.
g. How about this one?
Negative J.
Minus 1.
So this is, okay, it's a negative one, so it's minus g.
Minus J.
Okay. How about
Oh,
this?
sorry.
That's also minus J.
This is also minus g. What about this one?
That's J.
That should be g. Now we can compute all of them together, right? So this one is the same thing, almost, you can combine them together, right? So you get j times z1 minus j, which is plus z1, right? Something like that. So let's see what we get. So here we'll have something like that. Let's simplify a little bit more. So what is z thing? Can we name it?
Minus K? Well,
No. Let's take some examples, okay, so it will be easier to see what is that. Let's say k equals to 0, what it will be? 1. K equals 1,
it would be negative one.
negative 1, 2, get 1, negative 1, 1, and so on. So it's 1 minus 1, 1 minus 1, jumping. Can you write that as an equation or some sort of analytic thing? Formula? Or
Alternating.
interchanging 1 minus 1?
Alternating.
Yes. So it's just minus 1 to the power of k. That's what it is. The same thing here, but with different sign. Right? Again, you're starting again with 1, this will be the same thing. Minus 1 to the power of k. Because it starts with 0, then it starts minus 1. I mean, if k equals to 0, this starts with what?
1.
Minus 1
Yeah.
goes here. So then goes pi. So it will be minus, let's say. Okay, so now we know that we can write it in much more simplistic manner. So it will be j from here times minus 1 to the power of k plus j, all the same thing, minus 1 to the power of k, which is basically twice the same thing. And then let's start with minus. Add some minus here. We'll have 1 over 2j pi 1 plus 2. And then you have minus j times minus 1 to the power of k minus j minus 1 to the power of k. Which is again twice the same thing with minus sign. Now let's cancel out some terms. So first of all you have j here and j here, right? And j here. You can cancel this one with those two. You can cancel z minus with those two. Right? Just just replacing minus with plus on all of them. And this is why you need algebra basically to compute those things. Now you have minus 1 to the power of k plus minus 1 to the power of k. It's twice minus 1 to the power of k, right? So you can cancel this 2 with one of them. Just canceling 2 and 2. So this one will be twice minus 1 to the power of k divided by z2, right? So canceling z2 and leaving only minus 1. The same thing is here, right? So we canceling this one, and this one, and you canceling half of it with z2. And let's see what we've got. Let's see if we have place for what you have got. Let's try to move here. So that thing equals minus 1 to the power of k divided by pi 1 minus 2k plus minus 1 pi 1 plus 2k. This is basically what we've got. Now, can we simplify it even more? So we simplify it even more.
It's going to be plus minus
Any question on that?
with j.
So I basically canceled,
So the minus is plus.
I canceled j here and I canceled 2. Instead of sum of 2 equal things, I left only one of them because I canceled that with 2. And the same thing on the upper one. Exactly the same thing. Okay, I cancel j with j and 2 with sum of 2 equal parts. And left only one of them, which is minus 1 to the power of k. So it's like, that's right. Now, can we simplify it even more? To get something more beautiful than that.
Maybe we could factor out the minus a little bit.
After all, no, we need common denominator. How do we make common denominator to that thing? We need z1 times z1 somehow, and common denominator. So what it will be? So pi is common, of course, to both of them. And then you need z1 multiplied by z1. So what is that? How you compute? Remember that formula from algebra? That a minus b times a plus b equals a squared minus b squared. Very nice formula. Okay? So that's exactly what we are doing here. So you have something minus something times something plus that something. Right? So it will be 1 squared minus 4k squared. This will be common denominator. Okay? Now you need to find what you're multiplying here and what you're multiplying here. So it's minus 1 to the power of k times 1 plus 2k plus, again, minus 1 to the power of k times 1 minus 2k. Right, so you multiply z1 by z1, z1 by z1. Yes?
Why is it pi squared?
Because pi is common here, here and here. You can take it out of that equation and then multiply it there. So, look, you have something multiplied by 1 plus something multiplied by 1, it will give you twice the same thing, right? Then minus 1, whatever it is, multiplied by 2k, and the same thing multiplied by minus 2k, they will cancel. So those things basically cancel. And this is what you will get. It's pi over 1 minus 4k squared on the top, and here you have just twice that thing. Just to remind you what we started to compute is CK. After half an hour of computations, finally got the coefficient. This is the coefficient. You started with the formula, applied it directly. The Courson signal signals and systems ended here, basically. And from now on, it's course on calculus. Okay? So my course is easy, right?
Signals and system in comedy, or?
Maybe is that diagram?
No validation.
Yeah, all of us just like, yeah. you-
Appreciate the confidence.
No, dude.
Okay, so we have the coefficients that we wanted to find complex Fourier series. Basically, complex Fourier series, you just put in that thing in that formula. So this is complex Fourier series. You're right. So x of t equals sigma k equals from minus infinity to plus infinity. So we go in the formula, which is twice minus 1 to the power of k divided by 5. 1 minus 4k squared. And then we multiply that by exponent k twice 5
More to do?
t. Done.
Oh, that, okay. We're just.
Oh,
I'm just copying it formally so that you'll have some answer. What is Fourier, complex Fourier series is that thing. This is complex Fourier coefficient. Okay, the
Okay,
computer-
then we write it back.
Now I just put it here.
That's it.
Well, we gotta find the
Yeah,
coefficient.
that's it.
That's it?
That's it.
So this is 10% of the test. Okay, now let's move to Zalman. Yes,
So are we gonna always be able to convert it to complex?
yes. We're always able to convert it to complex. Okay, so average value. Now easy life starts. Okay, average value. What it is? Can you compute average value here?
Are we on zero? Divided by zero.
Just see zero. What it is?
So fuck zero.
That would be is 2 over pi. This is your DC voltage bias for that kind of function. By the way, you can compute that as RMS. This is exactly the same thing. So if you compute in RMS to that signal, this is what you will get. This is relation to circuits. This is RMS of that signal.
Wow.
Exactly. How
That
important
worked for
how
just
to-
2 over classes.
How about obviously you don't want to compute that. For absolute value of cosine squared.
So then you have CK.
So it's not that difficult actually, in that case. But if you have something more complicated, no. All we need to do is to add all of the coefficients together. And then you'll have infinite sum. Do you want to try that? No. Again, look, I'm trying to bring here some common sense. If you see that question is near insolvable, you cannot solve it in 5 hours, right? Nobody will give you in the test to solve that kind of question using the method you're trying to use. This means only one thing, that you're using the wrong method. This is the only thing you can think of, right? And this is the right answer. You actually have to use the formula.
So our 5-hour problem. 3-hour problem.
So you convert it into that problem. So t equals 1, right? So you want, basically you can divide by 1t and then take it from 0.5 to plus 0.5. Basically that's it. So here you go. You get 1 over t integral from minus t half to t half of your xt squared. This is your problem, right? Let's see, it's not the problem. Actually, in that case. Minus 0.5 again to 0.5 as we had before. So what is that thing squared? Absolute value squared. It's the same cosine, right? It's cosine squared. So it's cosine squared by t. What is cosine squared by t? 1. You have the formula in trigonometric identities. The formula says something like that. Twice cosine square of theta equals 1 plus cosine of double theta. Twice theta. This is the formula. So essentially, if you want that one, you just divide in both
So it's
by 2. So you get integral 1/2 dt plus integral minus 0.5 to 0.5, 1/2 cosine twice t. Twice pi t. Which will give you, of course, 1/2 times how many? Can you compute that easily? So it's constant 1/2 in interval of 1. So what will be the integral of that thing? Just area under that rectangle of height 1/2.
Yeah.
That thing. Height 1/2. What it will be? 1/2. Yes.
1 times 1 half.
1 times 1/2, yeah. Still will be half of 1. Plus, integrating that thing you have in the table, or you can compute it. If you remember that this is basically sine, integral of cosine, so it's 2 pi sine of 2 pi t, and t runs from minus 0.5 to 0.5, and then you get essentially something very simple here. So why is that simple? Because what is sine of 2 pi 0.5? Sine pi, yes, so what is that? 0. How about minus 0.5? Also 0, so all of that part is 0. You don't care. What left? 1/2. Exactly. That's it. This is the problem. It's not that horrible.
Turn the wires. We need it. So, I get it.
Okay, how about computing spectrum? This part is fun. Computing spectrum, let's see. Yes. So spectrum is absolute value of that thing, and you want to plot. So we found that ck equals twice minus 1 k divided by pi 1 minus 4 k squared, right? I remember it by half now.
This is spectrum.
This is spectrum. And you want amplitude spectrum, which is ck absolute value. And you also want probably envelope ck, which is phase spectrum. And you want to plot it. How do you plot it? Let's see. First of all, we don't have to plot the left part because left part is symmetrical with regard to right part. If you're looking at k, doesn't matter if k is positive or negative, it will go exactly the same symmetrical mirror way, right? Because here k is squared, and k or minus k will give you the same kind of thing, right? So, absolute value of z, what it will be? So ck absolute value will be just absolute value of minus 1 to the power of k is basically 1. So it will be twice 2 divided by pi, and absolute value of 1 minus 4k squared. Something like that, right? Now, how can you plot that? You can simplify that. What is the sign of that thing for k equals 0? Positive, right? For k equals 1, 2, 3, 4, and so on, it will be negative, right? Because 4 is bigger than 4k is bigger than 1. So for everything except k0, this thing will be negative. So you need to flip it. So for k equals to 0, let's compute it directly. It should be, what is that thing? Over pi, we computed that already. And for k larger than 0, we will have twice divided by pi 4k squared minus 1. I want to get rid of absolute value here. That will be easier to plot. So I can plot that thing already here. This will be my ck. And the initial value is 2 over pi. It will start somewhere here. Whatever the value is, 0.6 something. Okay, now let's compute it for k equals 1, for example. So it's twice divided by pi, 4 minus 1. So it's 2/3 divided by pi. Probably somewhere here. That's the second one. How do you know how it will go for larger k? How it will go for k larger than 1, much larger than 1? How it will look like?
10.
You're really close to 0.
It'll go to 0.
It will go to 0. Why? Because when k
By
goes to
constant,
infinity,
by-
that thing goes to 0. But as which function? Like, can you name the function? How it should look like?
Right.
Look, when k is very big number, 1 will be ignored, right? So that ck absolute value will be approximately equal to twice divided by pi 4k squared. So you can cancel that one with that one. So it will be 1
Over 2 pi
over
k squared.
2 pi k squared, approximately. When k is large enough. That's how you make approximations. Because ignoring that one compared to 4k squared, which is big number. So what is that? So the square of hyperbola. It goes somehow like that, to 0. Or very close to it. It will never go to 0, but it will go down like that. And so on. Okay, and this will be k. 1, 2, 3, 4, 5, and so on. How about angle? Phase spectrum. How it should look like? Let's take a few examples. K equals to 0, k equals to 1, k equals to 2, and so on. So k equals to 0. What angle do we have? So it's something positive divided by something positive. What is the angle of that thing? Right, so if k equals to 0, we get something positive divided by something minus 0, which is pi. So it's 2 over pi. So what angle 2 over pi has? No, it doesn't translate with 2 over pi. So what angle it is? Any positive real number.
2 over pi.
What is angle of any real positive number?
9 or 0?
It's 0.
0, 0.
Any negative number is pi, minus pi. Any positive number is just 0. So here angle of C0 is 0. How about 1? So it's negative divided by something which is minus 1 squared, it's not minus 1. 1 squared is just 4, 1 minus 4 is negative. So it's negative divided by negative. Again, positive. Again, 0. The angle is 0. How about 2? So it's something positive divided by something negative. So pay attention that after 1 it always will be negative, right? So this part will be always negative. Upper part will flip. Positive, negative, right?
So negative pi.
So negative, positive pi.
Well,
And then it will be
or negative pi.
0. You won't have negative pi. It's flipping from 0 angle, which, like if it is positive, this is 0 angle. If it is negative, this is pi. Or negative pi, whatever. Negative pi and positive pi is the same thing in angles. It doesn't matter. So it will be 0 pi, 0 pi, and so on. All the time. So you will start with 2 zeros, like that, or 0 and 1. And then you will have pi, 0, pi, 0, pi, 0, and so on.
So all that pi.
This is how it looks like. This is pi. This is spectrum. Jumping from 0 to pi except the first two. Any questions?